Hey, focused learners, and welcome to The Explainer. Today, we're totally cracking the code on algorithmic optimization. We're going to be digging into two absolutely crucial concepts, hash maps and prefix sums. Now, if you've ever stared blankly at a coding interview question about arrays and just wondered, how on earth do I avoid those dreaded nested loops? Well, you are in exactly the right place. We're going to take your beginner brute force code and transform it into highly optimized linear time algorithms. Let's get right into it. Okay, so here's our roadmap for today. We'll look at the big data problem, then dive into hash maps and sets, explore prefix sums, tackle sum zero subarrays, level up to sum equal to k, and finish off with a complexity review. All right, section 1, the big data problem. We've got to start by asking ourselves exactly why our standard everyday lists just fail us in the real world. Why can't we use a simple list for everything? Well, imagine you're building a system to track occupied hotel rooms. Tracking 5 occupied rooms with a basic list? Simple enough. You just scan the list from start to finish. But what if your hotel has 1,000 or even 10,000 rooms? Scanning that entire list every single time a guest checks in or out? Yeah, that becomes a massive bottleneck. Relying on slow searches when you actually need instant answers is a classic beginner mistake when dealing with big data. Moving to section 2, hash maps and sets. So to solve that hotel room dilemma, we need instantaneous access, right? And that brings us to the real foundation of hashing. Now there's a clear and super important distinction here. A hash map acts like a highly organized dictionary. It stores data in key value pairs, linking a specific unique key directly to a value. A hash set, on the other hand, drops the value entirely. It only stores unique keys. It basically just cares if a unique key exists at all. Fun fact, behind the scenes, a hash set is literally just using a hash map internally. But both of these are going to give us that average constant time performance we so desperately need. Let's look at a practical example. Imagine we're mapping a country, which acts as our unique key to specific values, like its population in millions or its number of states. In a hash map, if we look up the key India, it instantly connects us to the value 145 million for population or 29 for states. We just completely bypass the need to scroll through an entire table row by row. It's an instant lookup. Now, the trade-off here is order. Whether you're querying for India or the USA, hash maps don't maintain a specific sequence. They are totally unordered. But in exchange, they guarantee average constant time retrieval, big O of 1, regardless of the country key. This completely sidesteps the risk of collisions, slowing us down as our data sets scale up. So the really crucial point is how we apply this to array problems. Check out this frequency counting challenge. If you're given a massive target array and asked a bunch of queries about how often certain numbers appear, doing a full scan for every single query is just impossibly slow. Instead, what we do is iterate through the array just one time to build a frequency map where the number is the key and its frequency is the value. Once that map is built, we can answer any subsequent query, like how many times does the number 8 appear, instantly. For coding interviews, this is an absolutely vital optimization trick. All right, section 3, prefix sums. Now that we've got instant lookups down, let's introduce our second core concept to complete our toolkit. Think of a prefix sum as a running total of your array. Instead of looking at individual elements, it's an auxiliary array that allows us to compute any continuous subarray sum in constant time. Basically, by storing the sum of all elements up to the current index as you go, you ensure you never have to recalculate a continuous block from scratch. And here is the golden formula you absolutely need to memorize. The sum of elements from index A to index B equals prefix B minus prefix A minus 1. Combining this constant time math with our hashing trick, that is exactly what unlocks incredibly efficient modern coding solutions. Section 4, Sum Zero Subarrays. Let's synthesize these tools to tackle our first major interview challenge, finding out if a continuous subarray exists that sums perfectly to 0. If you use nested loops, you're stuck in quadratic time. But with our new tools, the logic is absolutely beautiful. Step 1, calculate the running prefix sum. Step 2, check your hash set for that current prefix sum. Step 3, if a duplicate is found, a zero-sum subarray exists. Think about it mathematically. If we see the exact same running total twice, it guarantees the numbers between those 2 points completely canceled each other out to 0. We just drop each prefix sum into the hash set as we go, and if we hit a duplicate, boom, we found it. Section 5, Sum equal to k. We can easily escalate this logic. What if the interviewer tweaks the question and asks for a target sum? Let's call it K instead of 0. The mechanics are almost identical. Step 1, define the target sum as K. Step 2, calculate the current prefix sum. Step 3, check if the current prefix minus K exists in the hash set. We're using a simple algebraic trick here. If our current running total is 15 and our target K is 5, we just look in our hash set for the number 10. If 10 is in there, we know for sure a subarray summing to 5 exists. But here is where the interview can get really tricky. What if they ask for the actual count of all possible subarrays that sum to K, rather than just asking if one exists? Well, counting subarrays requires a hash map. A hash set isn't enough anymore because it only stores unique values. To count frequencies, you have to upgrade. Don't make that beginner mistake. Let's dry run this exact logic. 1. Calculate the prefix sum as usual. 2. Check the map for our required counterpart, which is the prefix sum minus K. But this time, if we find it, we don't just return true. 3. We look at the frequency value stored in the map, and we instantly add that frequency to our final tally. 4. Update the map with the current prefix sum. We do all of this in a single, elegant pass through the array. It is a real game changer. Finally, Section 6, Complexity Review. We've covered a lot of serious ground today, so let's run a quick performance check. By trading just a small amount of memory to store our hash maps and hash sets, we've successfully and completely eliminated nested loops from our code. Instead of sluggish O of n squared time complexity, we are at O of n, a highly optimized linear time complexity, meaning we just have to walk through the dataset one time. As our source material points out, this technique ensures that the solution remains efficient by reducing the need for nested loops. And honestly, that perfectly illustrates our real goal here. Mastering efficient data structures is exactly what bridges the gap between slow, beginner brute force code and those elegant, interview-winning algorithms. So, I'll leave you with this question. If hash maps and prefix sums can optimize array challenges to O of n time, what other slow, nested loops in your own code could you optimize today? Keep that in mind as you head into your next coding session. Challenge yourself to hunt those down. Thank you so much for joining me on this Explainer Focus Learners. Keep optimizing, and I'll catch you in the next one.